Black holes, the ultimate cosmic monsters. We are in awe of them, we fear them, and at times we even revere them. With good reason. We know of nothing else in the universe that comes close to their destructive power. They can tear apart stars, dismantle solar systems, and warp the very fabric of space-time itself. But what if, lurking behind that apparent omnipotence, is a far more sobering truth? What if we need black holes? Or at least, the universe does? Because perhaps without them, reality would begin to lose something essential. Its internal consistency, its ability to make sense of itself, and ultimately, its ability to exist as a single, coherent whole. This is Dark Beacon. And in this video, we're asking a question physicists have wrestled with for decades. What exactly are black holes doing with the universe's information? And why should we care? To understand why black holes behave the way they do, we first need to be clear about what an event horizon actually is. It's easy to imagine it as a physical surface, a boundary you hit, a place where something dramatic happens, but that picture is misleading. An event horizon is not an object, it's a rule. Specifically, it's a rule about information. Once something crosses an event horizon, no signal it carries can ever reach the outside universe again. Light can't escape, messages can't escape, cause and effect stop flowing outward. But here's the crucial part. For the observer falling in, nothing special happens at the horizon at all. There's no wall, no sudden force, no moment where physics breaks down. Everything continues normally. Meanwhile, for a distant observer watching from far away, the story looks completely different. They never see anything cross the horizon. Instead, they see information slow down, stretch out, and fade into something that looks increasingly like heat. Already, reality is being described in two incompatible ways. One observer says the object continues on its journey. The other says its information has effectively vanished from view. Physics tolerates this, but only because those observers can never compare notes. Horizons don't just hide things, they enforce limits on what can be known, by whom, and when. And that makes them one of the most dangerous features a universe can contain. Now let's consider the scenario physics cannot allow. Imagine that information survives a black hole's horizon intact, not just in some abstract global sense, but locally, structured, readable, usable. Inside the horizon, objects would still have internal states, memories would still exist, correlations would still mean something. In other words, there would be a definite physical answer to the question, what exists right now? For the infalling observer, nothing would appear lost. The past would still have structure, events would still leave records, cause and effect would continue normally. But for the distant observer, that same information would not exist in any usable form. From the outside, the black hole would have already erased every distinguishing detail, reducing everything to mass, charge, and spin. These are not two descriptions of the same fact. They are two incompatible claims about what physically exists. One observer says a structured state is real, here and now. The other says no such structure exists anywhere in the universe. At that point, the problem is no longer about observation, it's about existence itself. If intact information can survive behind a horizon, then reality stops being a single, coherent thing. It fractures into versions that depend on where you stand, and physics does not survive that move. At this point, a reasonable objection appears. You might think this doesn't actually matter. After all, observers on opposite sides of a horizon can never communicate. They can never compare notes, so why should it matter if they disagree? The problem is that physics doesn't just describe what observers can measure, it describes what exists. Even if two observers can never exchange information, The universe itself still has to evolve according to a single, consistent set of rules. There must be one global description of reality that works for everyone, everywhere. Quantum mechanics in particular depends on this. It requires information to be conserved. It forbids information from being duplicated or deleted, and it does not allow physical facts to depend on who is looking at them. If a structured state exists for one observer but does not exist for another, then the universe no longer has a single account of what is real. It is split into incompatible versions of now. That kind of disagreement can't be patched over by saying no one will ever notice. Unobservable contradictions are still contradictions. Physics isn't allowed to say it doesn't matter because no one can check. Its laws apply globally, not operationally. So the issue isn't communication, it's consistency. And once horizons are allowed, consistency becomes fragile. Think of the universe like an operating system. Different programs can run in isolation. They don't need to talk to each other, but they all depend on the same underlying OS. If one executable says a file exists, and another says that same file doesn't exist, the system isn't showing different perspectives, it's corrupted. Even if those programs never interact, the operating system still has to be internally consistent. Physics works the same way. Reality can't disagree with itself, even in places no one can ever access. If you're enjoying this, it really helps to let me know. Dark Beacon is a small channel, and every interaction genuinely makes a difference, so if you feel like it, leave a like, and if you've got thoughts or questions, drop a comment. I read them all, and I always respond. Now, let's continue. This is where black holes stop looking like problems and start looking like solutions. Because black holes don't allow information to survive a horizon in a stable, usable form. They don't preserve structure. They don't preserve identity. They don't preserve readable history. Instead, they shred it. Anything that falls into a black hole is broken down into its most basic properties. Details are erased. Distinctions disappear. What made one object different from another is lost. What remains is information that still exists, but no longer means anything locally. It is smeared out, scrambled, and distributed so completely that no observer can reconstruct it into a coherent story. Think of it like discovering an ancient text. The symbols are still there, every mark is intact, nothing has been erased, but there's no Rosetta Stone. You don't know the language, you don't know the grammar, you don't even know which way to read it. The information exists, but it has no meaning you can recover. This is not destruction in the usual sense. Nothing is deleted, nothing is duplicated. The bookkeeping remains perfect, but the structure, the part that could create disagreement, is gone. By shredding information into non-local correlations, black holes ensure that no observer retains privileged access to the past. No one gets to keep a private archive behind a horizon. The universe keeps the data, but it takes away the key, and that turns a dangerous contradiction into a stable rule. At this point, it's natural to ask where the information actually is. If it isn't destroyed, and it isn't preserved as usable structure, then what does that even mean? The mistake is to imagine information as something that must live in a place, as if it's stored somewhere inside the black hole, waiting to be accessed. Modern physics suggests that picture is wrong. The information isn't sitting at the centre, it isn't hidden behind the horizon like a locked archive, and it isn't stored in any local, readable form at all. Instead, it exists only as global correlations, spread out so completely that no single observer can isolate or reconstruct it. No part contains the story, only the total pattern does. And crucially, that pattern is not something any observer can use. It can't be accessed, copied, or turned back into a meaningful record of what fell in. This is how information is allowed to survive without causing trouble. It exists, but nowhere it can do any work. Nowhere it can anchor a privileged account of the past. The universe doesn't lose information, it makes it causally harmless. And that distinction turns a paradox into something far more stable. So if the information isn't stored, and it isn't readable, what is it actually doing? From the outside, a black hole looks simple, but internally, it behaves like one of the most chaotic systems physics allows. Information that falls in doesn't settle, it doesn't freeze, it doesn't wait. It is continuously mixed, spread, and re-entangled across the entire system. Physicists describe black holes as extreme scramblers, among the fastest known. Any trace of structure is rapidly diluted, not just hidden, but actively erased as a usable pattern. This scrambling is not random destruction, it follows precise quantum rules. Correlations are preserved, but they are distributed so widely that no subset of the system retains meaning on its own. In some theoretical descriptions, this process resembles the way information is protected in quantum error-correcting codes. Not because the black hole is computing anything, but because the same mathematics appears when information must survive without being locally accessible. The result is information that still exists, still evolves, and still obeys conservation laws, but can no longer influence events in any coherent, directional way. It has been rendered causally inert. This is how information can be preserved without becoming dangerous. It remains part of the universe's accounting, while being prevented from anchoring history, memory, or disagreement. Scrambling doesn't erase the past, it dissolves it into correlations that no observer can turn back into a story. If information is preserved, then one final question remains. Does it ever come back? For a long time, the answer seemed to be no. Hawking radiation appeared perfectly random, a slow thermal leak with no memory of what created it. But over the past decade, that picture has changed. Modern calculations suggest that while early radiation carries almost no usable information, later radiation does. Not as images, not as messages, but as subtle correlations spread across vast amounts of emitted particles. In principle, the information isn't gone. It's leaking back out, but in a form so scrambled that reconstructing the original history would be practically impossible. What returns is not a record of events. It's not a story. It's not meaning. It's raw bookkeeping. The universe gives the data back, but only after it has been stripped of everything that once made it intelligible. This matters because it means black holes don't violate the rules of physics by destroying information, and they don't violate consistency by preserving it in a usable form either. They do something subtler, they delay it, they disperse it, and by the time it re-emerges, it can no longer anchor disagreement about what once was. The paradox isn't resolved by choosing between loss or preservation, it's resolved by transformation. Seen this way, black holes stop looking like cosmic destroyers. They become something else entirely. In a universe that allows horizons, forgetting is not a failure, it's a requirement. Information can survive, but meaning cannot be allowed to cross causal boundaries intact. If structured history were preserved behind horizons, reality would fracture into incompatible versions. Different observers would inherit different pasts, and the idea of a single, consistent universe would collapse. Black holes could prevent that outcome. They don't erase information, they strip it of the structure that could create contradiction. They convert history into statistics, memory into correlation. What survives is enough to keep the laws of physics intact, but never enough to give any observer privileged access to the past, present, or future. If that is true, black holes are not monsters lurking at the edge of reality. They are enforcement mechanisms. They are how the universe protects its own coherence by learning where and how to forget. And in doing so, they reveal something quietly unsettling, that consistency may matter more than meaning. We tend to think of forgetting as a flaw, as something that weakens systems, something to be corrected. But in a universe as vast and violent as ours, forgetting may be what keeps reality from tearing itself apart. Black holes don't just consume matter, they consume certainty. And without them, the universe might remember too much to remain coherent at all.